12, 8, 9. I think it's 9, right? And f of 2.05 is whatever the hell it is. Yes, 9. 8 plus 4, 12. Minus 4 is 8 plus 1 minus. Say again?
I think it's 9.717.
9.71.
7625.
All right.
Yeah.
So then, of course, you get 0.717625. That's the actual change in y. So let's use this one. So first I have to figure out f prime. What's f prime? 3x squared. 2x minus 2. And what's f prime at, in this case, 2. Yeah. 2 is the original thing. F prime at 2 is? Yeah, so you get 12 plus 4, right? 3 times 4, 12, plus 4, 16, minus 2. I get 14. Cool. And then, what was the other? Yeah, okay. So now this, how much did the x change by? That's the part I got right. Oh, it's right here. 0.05. So this will be f prime at 2 times how much the x changed by. So this is 14 times 0.05. That's how much the x changed by, right? So I get, for this, I get 0.75, I think. Yeah, right? Or is it 0.7, sorry? Half of 14 is 7. 0.7?
Yeah.
Okay. So the x changed by 0.05. The slope at 2 is 14, meaning every time I take a step in the x direction, it changes by 14. So if I multiply this by how much of a big step I took, I should get an estimate of how much y changed. Is that decently close to that? Yes. Why are they decently close? Because that was a relatively small difference. And it's a relatively well-behaved function. This is, what kind of function is this? Cubish, I love it. That's what it looks like. It's polynomial. Polynomials are well-behaved. That's a part of their definition. They are well-behaved, right? Meaning they don't have like a trillion oscillations within a short time or whatever like that. They don't have these cusps that do weird shit, right? They're well-behaved, maybe. So those are two different ways of getting estimates of change in outputs given a difference in input. So when I say the total differential, so later in this course, do you see how it's interesting how this goes straight to here? It's sort of like a chain rule almost in a way. Is that I have to multiply by the change in x. So if I had like u equals 7x, du would equal 7 dx. Do you see that idea? That's the idea of a total differential. This thing I just did is going to rule our life very soon. So that's why I like them introducing this now. So when we do it later, it's like, oh yeah, it's just the same old shit we did before. Baby. Okay, so let me see what time we got. Do you guys want to break already, or yes? Like, no? Keep going. All right, let me do a little bit more. The nice thing with Section 311 is I'm not going to make you do a lot with it. I just want you to know they exist. I need you to know the basic definition of these two things. Yes?
So the quiz isn't on 3.8, right?
No 3.8. Yeah. No 3.8. So this is so what are trig functions based on at the heart? Don't even bring a triangle into it, because where's that triangle that we use? Where does it come from? What are trig functions values based off of? Truly, I know we say triangle, which is true. It's ratios the size of triangles. But where does that triangle live in at the very beginning? The unit circle. I like it. So trig functions, our normal trig functions are based on circles. You could create trig functions based on hyperbolas that have the same kind of relationships that the trig functions based on circles do, and that's why they're called hyperbolic trig functions. Okay, we're not going to do freaky shit. I'm not going to make you draw hyperbolas and derive all these. I'm not. I'm just telling you this is interesting. You can Google some shit if you want to get deeper into it. All I want you to do is to know that they exist because they are useful as shit. They're used in a lot of different places, which is why I don't understand why some of my colleagues pass it by. And you have to know the basic definition. So here's how hyperbolic trig functions look. They got a little h in them for the hyperbolic, and we pronounce this sinh and cosh. So the sinh is defined to be e to the negative x plus e to the x, all over 2. And the cosh, I always forget, wait, e to the x minus e to the negative x all over 2. So let me write this one this way. This might make it easier to remember. Oh, I got those backwards, didn't I? Here's the thing. I always remember, what always keeps me in check is that cosh is an asshole. So if he has a choice, he's the one that's going to take the plus. He's going to make the sinh take the minus. That's just a definition, by the way. This is, well, it's more than just a definition, but it's, they do come from hyperbolic trig, but also, there's another reason why we call this grouping of things, we give it a single function name, is because they follow in weird ways the identities and the derivatives of sine and cosine. So they act a lot like their trig function. Now they're not perfect. They're not, in fact, take a minute. Can you guys figure out what the derivative of sinh is? Do it. Should be relatively easy because it's based on e's. Gotta love that shit. Please don't make it a quotient thing, right? I mean, this is just 1/2 e to the x plus e negative x. Not plus. I'm trying to give you a plus. That should be barely worth your time to do it. So what is it going to be? You should be done. It's 1/2. What's the derivative of e to the x? E to the x. What's the derivative of, so that's going to be minus, and what's the derivative of e to the negative x? Negative e to the negative x. So this is 1/2 e to the x plus e negative x. Well, what is that? That. Oh, so the derivative of sinh is cosh. Do you guys see that? Is everybody cool with that derivative? Is everybody cool with that derivative? It's e's. So I'm going to answer for you. Yes. It's exponentials. Holy shit, right? And isn't that this? Isn't this this? So the derivative of sinh is cosh. You might be tempted to assume to claim that the derivative of cosh is going to be negative sinh. You'd be wrong. Do the derivative of cosh real quick. This is one place where they're definitely different. Try to do the derivative of cosh. Basically see where this is going to go, hopefully. You really shouldn't have to do a lot of work. That's going to stay the same, right? This is going to have a negative come down. And this is equal to sinh. So it's not negative sinh, it's just sinh. So that's one little place where they're different, but it's close enough that we decided to give it symbols exactly like sine and cosine. Now, I've assigned homework that uses more than this, but this is the only thing I expect you to memorize. Do you understand? They go into derivatives of inverse hyperbolic trigonometric functions. I don't remember that shit, so I'm not going to make you remember it. You understand this? Whatever I don't personally remember, I don't ever make you remember. Sort of like the nice gym teacher that only makes you do shit that he could actually do. Which I'm sure you've had people that couldn't sit there drinking their tea. I had a dude sit there drinking his tea, have it plopped on his belly, and we'd be running around the track. Anyway. So that's section 311. There's homework. They reference formulas in the section. It really shouldn't be that evil. I just want you to be aware that these exist. The most famous use of well, this one specifically, is the shape that a cable takes if you put it, if I tied a cable here, I tied it there, and you try to make it tight, it's never going to be straight. It's going to take on this kind of shape here, right? This shape is describable using this. It's called a catenary. Have you ever heard of that before? If you look at phone, phone poles or like power, they kind of like that, right? And I don't care how tight you try to make it, it's always going to have that bend in the middle. It's going to follow, and you use this function to describe its shape. Okay, so that's one example. They give you a nice little picture at the bottom of page 259 of some cable. All right, so now let's take a break now. We'll just finish chapter 3. I think we can take a break. Why don't you guys come back at 2? That's perfect. Cool. Okay.